Hello, this video is for Stat360 Handout 9 Part B, and it's going to cover pages 11 through 19. So Part B is included in the Google folder for Handout 9. In Part A, we considered the concept of leverage, which meant we were an outlier in the x direction, or one of the predictors was an outlier. In Part B, we are going to consider the notion of outliers, and that is going to be an outlier in the response direction, or the y direction. We also have a statistic called Cook's distance, or Cook's influence, which is a combination of leverage and outliers, and that will be discussed at the end of this handout. Okay, so let's go ahead and get started here. We're looking at a model that is for the price of Ford Focus vehicles that have at least 5,000 miles. And this model is going to use miles as the predictor variable. So we can go ahead and fit that model over here in Jump. So this data set is included in your Google folder for Handout 9. Analyze, fit model. Price is my response, and my predictor is going to be miles here. In Part A, we were using age as the predictor, but in Part B of this handout, we'll be using miles. Go ahead and click Run. Here's all my regression output, my summary of fit output, etc. And what we are going to be concerned with are observations here that are extreme in the y direction, in the vertical direction of our plot. Okay. So a crude measure of whether or not you're an outlier is to simply take 2 and multiply it by our root mean square error value, or our sigma hat value. Now this is the standard deviation in the residuals. It's the estimated standard deviation in the residuals. And if we go 2 standard deviations, so that's about just about $2,500 or so, a little bit short of $2,500. If I go 2 of those, that's going to be about $5,000. So a crude rule for an outlier is just whether or not my observation is more than 5,000 away from what I expect, or less than 5,000 away from what I expect. And I can pick this up just on the plot of the residuals versus predicted. I can snap a line here at about 5,000 and negative 5,000. And any observations that sit inside of these outlier bands here would be considered outliers. So you can see that I have a set of observations here on the high side that would be outliers. Now, where are those observations on the original plot? Well, they're going to be right here. So on the left-hand side, these Ford Focus vehicles are quite expensive. Overly expensive, I guess we would say, because they are outliers in the positive direction. So these points here, you can just highlight those if you want on the plot, and then you'll be able to see those highlighted on this plot as well. Now, as I said, that's kind of a crude rule. If we worry a little bit more about, or a little bit more careful about the distribution of the residuals, we'll find out that the expectation, okay, we expect the residuals, so this is just the residual vector here. The expectation or average value of those would be 0. So that just means that my residuals are centered about 0. And the variance or standard deviation is given by this quantity here. So we can do a little bit of matrix algebra here. And it turns out that the variance or the variability in the residual vector has a sigma squared in it, but also it has these hat values that we talked about previously in Part A of this handout. So this is actually a matrix here, okay, because this is a residual vector here. So the variability, or if we want to take the square root of that, the standard deviation of my residual vector is a function of the hat values. There's some general comments about those. That expectation holds when there's an intercept term in the model, which there almost always is. This I minus H matrix, that identity minus the hat matrix, is called a symmetric idempotent matrix. And what idempotent means is just if you multiply by itself, you're going to retain the same matrix. Okay, so let's talk about the idea of a studentized residual. So there's different types of residuals that we are able to calculate here. And this first one is the most common, and that is the studentized or standardized residual. To studentize a measurement, all I need to do is take the measurement minus its mean and divide by the standard deviation. This is just a z-score idea. If normal theory holds, when this quantity is bigger than 2 or less than minus 2, I'm going to be unusual, or I'll be an outlier. If you have non-normal data, we usually use 3 for that cutoff. And that's kind of coming from an idea called Chebyshev's inequality. So these are just z-scores. Anything above 2 usually is what we use, or below a negative 2 would be considered an outlier. A studentized residual in the context of a regression model is going to look like this then. It's going to have the measurement, which is just the residual, minus its mean, which is 0 from what we learned up above, divided by the square root of the variance. Or this quantity on the bottom here is going to be the standard deviation. And you can see this utilizes or involves the hat value. Again, that's coming from this quantity right here. We know that the variance in the residual vector is a function of the hat values. Now this is the variability here, or the variance, so I want to take the square root of this quantity when I'm trying to standardize, or use that quantity to standardize. Now JUMP obtains or computes this value for me. So inside of JUMP, from my red drop-down menu, I can say Save Columns, and then select Studentized Residuals. And that's exactly the quantity that it's calculating. So over here in my model, from my drop-down menu, I can say Save Columns and select Studentized Residuals. I can also get the hat values here if I wanted. I mean, I can get all these quantities. I can get the predicted values. Okay, I can get the residual values. I can get the hat values. And then the studentized values. And all of those things are being saved into my spreadsheet here. Okay, so if I go back and look in my spreadsheet, all of those extra columns are going to be included now. So all of these are just those values that are saved out. So here's an example of the data here where I have the predicted residuals, the hat values, and the studentized values. So you can go ahead and verify a task here is just verify that calculation for this 8th observation here. So this 8th observation, is going to have a large studentized residual. It's going to be bigger than 2 here, we can see. So here's just the residual. We have the variance, which is just going to be the root mean square error squared. So take that 2439 squared and you can plug that in there, and then the hat value here for that particular observation. We can see that when we do this, so looking at this column right here, the studentized residuals, I'm scanning down that list and just looking for any of them that are bigger than 2 or less than negative 2. And you can see that I have observations on the high side. I do have a couple on the low side, but they don't quite meet that threshold of negative 2. They're close, but don't quite meet that threshold. If I use the kind of the crude measure of 2 times the root mean square, 2440 times 2 is about 2448 here. Or 2440 times 2 is about 4800. So if I'm using the crude method, I just want to check to see if these residual values are bigger than the root mean, 2 times the root mean square error. And they would be for these 5, and they wouldn't be down here. So the crude method and the more exact method using this quantity here actually end up yielding the same set of residuals. And again, those are those on the high side. If we go back to that initial graph, it's those observations up there. Okay, so we have studentized. We also have what's called deleted studentized. And what the deleted studentized is about is that the model is computed, or excuse me, the root mean square error is computed without that observation in it. So a deleted studentized residual for a particular observation is computed from a model that is estimated with the observation deleted from the data set. So if an observation is withheld from the fitting process, then the residual may reflect a more pure notion of error in the prediction. So anytime you see these parentheses minus I, that just indicates that that observation has been excluded when doing the model. Again, we would use anything larger than 2 or negative 2. This the deleted studentized is sometimes called the externally studentized, whereas the studentized up above would be called the internal studentized. Now, JMP doesn't actually compute these externally studentized residuals, but you can get from the deleted or externally studentized to the internally studentized through the following. So just a little bit of algebra there. You can get from one to the other. The deleted studentized is not that common. Finally, we have the notion of Cook's distance. Now, Cook's distance is a separate measure of the effect of an individual observation by combining the idea of being an outlier with the idea of having leverage or high leverage. So Cook's distance is a combination of outlier and leverage. In this calculation, the RI value is the internally studentized, the HI value is the leverage, and K is just the number of X variables you have in the model. For our simple linear regression model, K is just going to be 1. An observation whose Cook's distance is substantially larger than the other should be investigated. And then Cook gives some general guidelines here. You certainly should look at Cook's distance bigger than 1. And also we have this idea of Cook's distance bigger than 4 over n observations whose Cook's distance is bigger than 4 over n deserves additional consideration. Now we can get these in JMP, so we can select from our drop-down menu here Cook's D influence, and those values will again be put out into our spreadsheet. So those would be over there on the right here. Now you're going to want to sort the observations with high Cook's distance. So you can do that real easily in JMP by just saying table sort. You want to sort by those values. Probably want to sort those in descending order here. So flip that arrow to being down and then say OK. And these values on the top are going to have ones that have high Cook's distance. And what I've done in the notes there is just highlighted a few of those that are worth talking about. So the orange ones here are observations that have high Cook's distance. The yellow ones are observations that have high studentized residuals and high Cook's distance. And then these blues actually have somewhat high studentized residuals, but not high at all in terms of Cook's distance. So these yellow observations, those 5 yellow observations, are still the 5 that we have selected there. It actually looks like this data point was put into the data set 3 times here. So that could have been from 3 different people giving me those values there. These are exactly the same miles. The price here is 20229 versus 20299. But it only looks like there's 3 observations there, but there's actually 5. Those 5 are indicated here with a yellow. These orange ones here, again, are going to have high Cook's distance, but not necessarily high studentized residuals. So these are going to be a little bit closer to the line, the orange ones, because they're not that much of an outlier in the Y direction. But they are somewhat of an outlier in the X direction. Especially this one down here is going to have high leverage. And these here are going to have somewhat high leverage. So those high leverage values are what's causing those Cook's distance values to be somewhat higher. Remember, Cook's distance is a combination of studentized residuals and leverage. These observations that are near the middle aren't going to have very much leverage at all, but they do come pretty close to being outliers. So this value right here is going to have an internally studentized residual of about 1.9, which is getting close to 2. This one down here is going to be negative 1.75 or so. So again, getting closer to 2. Doesn't meet the threshold. But these values here are not going to be indicated by Cook's distance because they have small leverage values. So Cook's distance is a nice way to combine the idea of leverage and being an outlier in the y direction. Okay, that does it for Handout 9 Part B. Thank you.